Assalamualaikum and good morning. I'm Huda from UKM. So this is the parallel section for section 4. So link 6. So for the first presenter, I would like to welcome Professor Dr. Hadinur from University Technology Malaysia, UTM, with the title Solid Oxide Fuel Cell for Power Industry. Okay, I think Prof can begin your talk.
Okay.
Okay.
So I will share my slide first. Yeah.
Yeah.
Okay. Thank you, Prof. Huda Abdullah. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Saya Hadinur. I will present a topic related to the fuel cell applications. There are 4 topics related to this project. The first is yttria stabilized zirconia thin film for solid oxide fuel cells electrolyte. The second is the preparation of the polybenzimidazole membrane for the proton exchange membrane fuel cell. The third concerns the carbon-containing titania-coated silane steel used for the proton exchange membrane fuel cell electrolyte. And the last one is related to the fuel cell educational kit. This is a new initiative from Program 1, which is a collaborative project under the Indonesia-Malaysia Research Consortium. In this study, for the solid oxide fuel cells project, we focus on solid oxide fuel cell electrolyte, because we know that the solid oxide fuel cells is short form is the OFC, known as the electrochemical device, which utilize fuel and air to produce electricity. Electrolytes are the most important components of the SOFC. We synthesize yttria stabilized zirconia thin film, which serves as the oxygen pathway. Yttria stabilized zirconia is a potential material used as an electrolyte for solid oxide fuel cells. The challenge is to produce yttria stabilized zirconia suitable for SOFC with a dense thin layer. So the criteria are necessary to have, number one is a cubic structure, non-columnar and AQX nanostructure, and without a pinhole. So in this project, we prepare yttria stabilized zirconia by using radio frequency magnetron sputtering. The parameters studied were oxygen flow rate, substrate temperature, substrate bias voltage, deposition time, and annealing temperature. We examine the relationship between the structure and properties of yttria stabilized zirconia resulting from this technique. Previous studies show that there was a stress and also texture development during sputtering of yttria stabilized zirconia films on silicon substrate, which resulting thin film not being a dense film. And it can reduce the efficiency of the yttria stabilized zirconia film for the oxygen mobility because it's not dense. This is a description of the preparation of the substrate and yttria stabilized zirconia target. The parameter of thin film growth processed by radio frequency magnetron sputtering that were studied were oxygen flow rate, substrate bias voltage, substrate temperature, annealing temperature, and deposition time. And then the sample is characterized using technique commonly used for the thin films. This is the effect of oxygen flow rate. We found that the formation of the crystalline yttria stabilized zirconia could take place in the absence of the oxygen gas. It can be seen that the structure of the yttria stabilized zirconia is the cubic structure with peaks of planes 111, 200, 220, and 311. This is the fourth is the major peak of the test sample. This is a FISM images of surface morphology and cross-section of the sample thin film. Yeah, this thin film sample prepared at 600 degrees Celsius in the absence of the oxygen. The thickness of film is about 200 nanometers. The substrate bias voltage also plays an important role in the formation of Yttria stabilis zirconia. It can be seen that the dense of non-columnar structure with a least microstrain is formed when using 120 volts of the substrate bias voltage at a temperature of 600 degrees Celsius. And the dense non-columnar structure was formed when the substrate applied with the 120 volt bias voltage at 600 degrees Celsius. It can be seen clearly if the sample is analyzed by atomic force microscope. We found that the structure and morphology also depends on the substrate temperature. In this slide, it can be seen that there is an effect of temperature on crystallite size and also lattice microstrain when heated at the various substrate temperatures. The atomic force microscope image shows a clearer picture of the substrate temperature dependent on the dependent on the structure and morphology, where the best result is obtained when heating at 300 degrees Celsius. Annealing temperature also plays an important role in the formation of Yttria stabilis zirconia. We observed that the maximum annealing temperature was 500 degrees Celsius. When we heat the sample above 500 degrees Celsius, there is a crack found in the sample. This is the atomic force microscope image Yttria stabilis zirconia annealed at a various temperature. And this is a FISM image of the sample, yeah, annealed at the various temperature from up to the 600 degrees Celsius. From the TEM image, the D spacing from peak 111 is clearly seen, with the value of the D spacing being 0.3 nanometer, which correspond to the XRD data. We also examine in detail the effect of deposition time. From the data generated, 1 hour deposition time is the best because it produces samples that have a good crystallinity. This slide shows the dependence of crystallinity on deposition time. By using the William Hall plot, it can be concluded that 1 hour deposition time will produce a sample that has a small microstrain. Okay, from the experimental results, yeah, it can be concluded that we have succeeded in controlling the structure of Yttria stabilis zirconia by varying the oxygen flow rate, substrate bias voltage, substrate temperature, annealing temperature, and deposition time. And also, we try to correlate between the structure and the properties. Okay, finish and project 1. If we go to the next project, is related to the proton exchange membrane fuel cell, namely the preparation of a line polybenzimidazole induced by magnetic field to be used as a membrane. This is a schematic diagram of the temperature proton exchange membrane fuel cell, where the main component of the TIS fuel cell is the membrane. Yeah, the membrane is placed between the anode and cathode, which contains platinum. Yeah, small particle of platinum, which act as a catalyst. To increase the efficiency of the proton exchange membrane, several strategies have been carried out previously. Among them is by adding nanoparticles and also by using electrospinning to produce a random aligned structure. One interesting method is to use particles that can align with the magnetic field so that the proton conductivity increase. In this study, we use polybenzimidazole, yeah, a material that is considered a potential proton exchange membrane. Firstly, many researchers or the commercially available, the material used for the proton membrane is Navion. So the topic of this project is to answer the questions. How to control the orientation of the polymeric structure of polybenzimidazole under magnetic field. Previously, we have experienced to align the titania particle by 5Cb liquid crystal. But in this project, we don't use liquid crystal because liquid crystal is volatile. It starts to evaporate at 70 degrees Celsius. Polybenzimidazole attract attention because this material has high thermostability, also low cost. However, pristine polybenzimidazole is pure proton conductivity and needs to be modified by adding additive or acid. In this research, we try to increase the proton conductivity by aligning the polymer with the magnetic field. And in this way, it is expected to create a proton conducting channel so that the proton conductivity is increased. I think that this is a new approach, to get a good conductivity, proton conductivity of the polymidazole membrane. We use a homemade magnet whose magnetic strength is 0.3 Tesla. The sample is placed between the north and the south poles of the magnet so that it is expected to polybenzimidazole can align with the magnetic field. The magnetic field induced alignment of the polybenzimidazole was prepared using the solvent casting method. This is the common method. The solution was cast and placed between the magnets with a magnetic strength of 0.3 Tesla, and the solution is allowed to dry under ambient atmosphere and is then ready to be characterized. The magnetic field induced alignment. Okay, the next step is to modify the polybenzimidazole membrane with phosphoric acid so that it can function as a proton exchange membrane. This is a very important step, to change its function as a proton exchange membrane. This is the atomic force microscope and FISEM image of the N-aligned polybenzimidazole. It means that there is no alignment with the magnetic field. It is observed that the proton conductivity of the sample is around 210 minus 6 Siemens per centimeter. When compared with the aligned polymizimidazole, the proton conductivity sample is about 610 minus 6 Siemens per centimeter. And its proton conductivity is, we can see that is about 3 times higher than that of the N-aligned polybenzimidazole. Atomic force microscope and FISEM show that this sample has been successfully aligned by the magnetic field. For me, that this result is very interesting because now we no longer need to add nanoparticle or another additive to increase the proton conductivity. Just with the help of the magnetic field, we can align the polymer chain and improve the proton conductivity. Okay, the next topic is a carbon-containing titanium-coated stainless steel, where this material is used as a proton exchange membrane fuel cell electrode. One of most of the challenging issue for the commercialization of the PAMFC is related to the bipolar plate because the plate may account for up to 80% of the total weight and between 25% to 45% of the total cost of the fuel cell stack. Under some fuel cell operating conditions, particularly at the anode, corrosion of the stainless steel might also affect the lifetime of the bipolar plate. In our study, we developed a new method, to deposit a carbon on the stainless steel. The carbon has a good anti-corrosion properties, that is to avoid the decay of the fuel cell after a long working time. The problem is how to attach the carbon. Yeah, in this case, it's a pyrolytic carbon to the surface of the stainless steel. This is because there is no chemical bonding between pyrolytic carbon and stainless steel. Another factor that occurs in the occurrence of the shrinkage during heating. Yeah, there are the things that cause pyrolytic carbon to be easily detached from the surface of the stainless steel. Yeah, and because there is only physical interaction between the carbon and stainless steel. So the aim of the TIS coating is to produce strong attachment of the pyrolytic carbon on the stainless steel. So in this study, we use the high voltage powder spray coating method by adding titania particle in the epoxy resin. Yeah, this is a commercially epoxy resin. And the hypothesis is utilization of the high voltage powder spray coating for the epoxy resin with the presence of the titania particle at certain process temperature can produce a good attachment of pyrolytic carbon on the surface of the stainless steel. Besides getting good addition, this project also studies the factors that contribute to strong adhesion coating. This is the fundamental studies. Yeah, why the adhesion is very good. There are a step in this research, yeah, from the preparation to studying the adhesion phenomena. We use commercially epoxy resin as source of carbon, as well as titania powder. The substrate used is stainless steel AISI 304 and use high voltage powder spray coating. High voltage powder spray coating system is based on an electrostatic charging methods. Use high voltage gun. The powders that come out from the gun tips are all negatively charged and have a strong attraction to the grounded substrate and deposit in there, so that we can see that the good addition, yeah, between the carbon and the stainless steel. The coating stage are the physical spraying and curing process. Yeah, this is to get attachment of the carbon containing titania attached to the stainless steel. The second stage is the preparation by varying the pyrolysis temperature in order to produce the best coating addition. Then proceed with the study of the carbon containing coated stainless steel properties and its addition performance. This is the thermal analysis of coating. It appears that epoxy resin start decompose at 300 degrees Celsius. The pyrolysis temperature was selected. This study is between 300 and 700 degrees Celsius. This is FTIR spectra, so the functional group of the coating materials. It appears that the peak functional groups are reduced and diminished by increasing temperature. Yeah. This is the surface morphology of the sample, heated average temperature. By using surface profile method, it is shown that if the temperature increase, the coating thickness decrease. This result is in a good agreement, yeah, in the previous research showed by the FTIR and also by FISEM, and we use also ADX result. So is a very good agreement with that. The abrasion test and the peel adhesion tests were used to evaluate coating adhesion performance. This is the result of the abrasion test, which shows that heating at a temperature of 300 degrees Celsius is the best temperature to produce a good coating. So carbon containing titania coated stainless steel heated at 300 degrees Celsius was used to study the adhesion phenomena. Coating adhesion performance of a carbon and also carbon containing titania coated on stainless steel at 300 degrees Celsius indicates that the presence of titania plays an important role in strengthening coating adhesion. From the peel adhesion test, it can be seen that titania particle plays a role in producing good adhesion coating. These are summary of the characterization. Epoxy resin was converted to pyrolytic carbon, started at pyrolysis temperature from 300 to 700 degrees Celsius. The formation of the pyrolytic carbon was proved from the color chain, functional groups, and also XPS analysis. The incorporation of titania has reinforced the coating adhesion. This is very important. Why? If you add the titania, the coating is very, very, very good. For that question, we use to elucidate the carbon containing titania coating adhesion phenomena. We have analyzed the sample by XPS. We have analyzed more than 40 samples by XPS. This is a part of the result of the XPL analysis. It is clear that the presence of the iron oxide on the surface of the stainless steel. And also structural change has been observed using XPS for the sample heated at 300 degrees Celsius. This temperature produces a strongest adhesion of the carbon on the surface of stainless steel. It is observed that the shifting of the carbon-carbon peak to higher binding energy and a strong interaction of the carbon-carbon near the surface of the stainless steel. From the carbon 1s peak, there is no structural change has been observed for the sample heated at 400 degrees C, which is the from the test sample, this is a weak addition. It is observed that no shifting of the carbon-carbon, suggesting that there is no structural change occurs. The same trend was also observed for the carbon containing titania sample heated at 500 to 700 degrees Celsius. So, the analysis of the carbon 1s peak of the XPS is very, very important. And it can be used as a clue to answer the question, why carbon coating in the presence of titania heated at 300 degrees C has the stronger adhesion strength. Here, it is clear that there is a shifting of the carbon-carbon bonding energy of the sample heated at 300 degrees Celsius. By plotting the relationship between the temperature and carbon-carbon bonding energy, we can answer the question, why heating at 300 degrees Celsius give a stronger adhesion? This is due to high binding energy of the carbon-carbon is related to the strong carbon-carbon interaction, which means that related to the pyrolytic carbon structure, related to the high shrinkage and resulting pore adhesion. We can imagine that if the binding energy is very high, so that the binding with the carbon-carbon is can correlate to the structure. It makes a high shrinkage. It is clear that the presence of titania helping in minimizing the carbon shrinkage. Supported by density functional theory calculations, DFT calculation using a model compound, it can be concluded there are the three factors affect the carbon adhesion. Number one is the presence of the oxide layer on stainless steel. We analyzed by XPS. Second, the presence of the functional group. And third, due to the structure shrinkage. So we found that the titanium nanoparticle reduces the shrinkage of the carbonaceous coating and improves the coating adhesion. So based on the result, it can be concluded that the interfacial interaction of the carbon containing titania coated stainless steel shows the three factors that affect the carbonaceous coating, known as the oxide layer, functional group, and the structure shrinkage. And this is the result. We published papers And our paper entitled The Carbon Containing Titania Coated Stainless Steel Prepared by High Voltage Powder Spray Coating and its addition phenomena, published in Progress in Organic Coating in October 2020, has been featured in the picture Furnici European Coating last month. Yeah, we proud that this work has been attract the attention from the company. Yeah, this is the picture Furnici European Coating is a consortium of the coating company based on in Italy. Okay, this is the last topic. It's related to the Fuel educational kits, a new initiative project from Program 1, which is a collaborative project under the Indonesia-Malaysia Research Consortium. Under Indonesia-Malaysia Research Consortium, we create a new project on innovation in science, technology, engineering, and mathematics, STEM. Yeah, we call it as a STEM learning media. The project is a joint project under this umbrella of the Indonesia-Malaysia Research Consortium. Our partner now is Universitas Negeri Malang. Yeah, so Dr. Siti Sendari also attend my talk today. The idea is to create an Indonesia-Malaysia Nanotechnology Research Cluster under the umbrella of the Indonesia-Malaysia Research Consortium. And we have the meeting. Yeah, this is the Gantt charts of the progress of the Indonesia-Malaysia Research Consortium, IMRC. We start with the 2016. Yeah, we have the Indonesia-Malaysia Research Consortium Forum in the UTM Kuala Lumpur. Second, there is a visit of the high-level group consists of the Minister of Higher Education of Malaysia, Datuk Seri Idris Yusof, to Jakarta to meet with the counterparts, the Ministry of the Research and Higher Education of Indonesia, Professor Nasir. And in 2018, we have the meeting to discuss on the project. One of the project is the innovation in STEM learning media. This is the fuel cells educational kit. This is our meeting at Universitas Negeri Malang on Indonesia-Malaysia Research Consortium project on educational kit. And this project, its coordinators is Professor Datuk Halimatun Hamdan from Malaysia and Professor Markus Diantoro from Indonesia.
I'm so sorry, Prof.
Yeah, okay. I have the two slides. Yeah, okay. I have the two slides. Okay.
You can continue.
Okay. So the objective of the program here to produce innovative teaching, to promote InQ-based curriculum, to evaluate effective learning tools, yeah, and so on. Now we are in the year 3. This project is still running and entering this year. There are the results, yeah. We developed the prototype of the fuel cell EduKit with the augmented reality. This is a project, is a collaborative project between UTM and Universitas Negeri Malang. Now, both university will provide matching grant to carry out this project. So, me develop the prototype of the fuel cell educational kit, and our friend from the Indonesia developed the fuel cell augmented reality. And last year, 2019, we saw, yeah, they demonstrate that these kits in Nano Symposium in 2019. Okay, that is the expected of this project, yeah. Renewable Energy STEM Educational Kit. We have impact assessment. I hope that this project will have global scale impact with research outcome, impacting international and future community. The long term of the objective is to be internationally recognized reference for the innovative learning media. Short term and medium objective is to develop, disseminate, apply knowledge, and so on. And this is also an instrument for network of excellent infrastructure. We already have the discussion G2G to how to become to force that this project is become big project under the umbrella of Indonesia Malaysia Research Institute. Okay, thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Now 29 minutes, yeah, I have the presentation.
Okay, never mind.
That's
Thank
the
you for
behind the
Dr.
schedule. Okay.
Okay, behind the time. Okay, it's okay. But we can continue for this. I think any question from the only, I think can ask for 1 minute question from the audience. Okay, if we don't have, can I continue for the second presenter?
Okay, thank you, Prahuda. Okay,
Okay, thank you, Dr. Prof. Hadi. Okay, for the second presenter, I would like to welcome Professor